Okay, hello. We're going to go through test 4. Hopefully, you did good on this test, but we'll see. There was a surprising amount of the same letter, so don't be too surprised when you see this letter keep coming up. But we'll work our way through. Hopefully, you'll learn something, be a little bit better prepared for the final. Starting with number 1. Sodium bicarbonate neutralizes acid via the following equation: NaHCO3, sodium bicarbonate, plus HCl goes to water, sodium chloride, and CO2. The carbonate, bicarbonate means HCO3, or sodium hydrogen carbonate. Now, how many grams of sodium bicarbonate would be needed to neutralize 25 mils of 6 molar HCl? So we're going to turn molarity of HCl to moles of HCl to moles of bicarbonate to grams of bicarbonate. The first step is to find the moles. So 6 molar times 0.025 liters would give us the moles, and there will be 1 mole acid per 1 mole bicarbonate. So 6 times 0.025 is we have 0.15 moles. Okay. Next step is to use the molar mass to find the grams of bicarbonate. Sodium is 23. Hydrogen is 1. Carbon is 12. Oxygen is 16. There's 3 of them. So 48 plus 13 plus 23, molar mass of 84 grams, 1 mole. 84 times 0.15 is 12.6. So first answer is B. B was used a lot. You will see a lot of B's. How many moles of gas would be contained in 1 liter vessel at STP? STP is a little contradictory, little standard temperature and pressure, 1 atmosphere, and not 298, but 273 Kelvin. Standard temperature is actually 0 degrees Celsius. So this is, instead of looking at how many liters would 1 mole contain, how many moles would be in 1 liter. So PV over RT equals N. So 1 atmosphere times 1 liter over R, 206, and temperature 273. Had you used the wrong R, you probably still would have got the same answer, but you have to use 273 to get the right answer. Otherwise, you get answer B. The correct answer is answer A, 0.045 moles. How much heat must be absorbed into 20 grams of tin, heat capacity of 0.228 joules per gram Kelvin, to heat it from 25 to 232 Celsius? So Q equals MC delta T. So M is 20 grams, heat capacity 0.228, and temperature change 232 minus 25. 20 times 0.228 times 2, the difference between 232 minus 25. You get 943, which 0.9, which rounds up to 944. Answer B. Number 4. What volume of 2 molar acid, HCl, would be needed to neutralize 35 mils of 1.73 molar KOH? 1-to-1 ratio. Simply MA VA equals MB VB. Pretty straightforward. 2 times V equals 35 times 1.73. Hopefully, there's only really one answer it should be, and that's going to be D, because the base is less concentrated than the acid, so it should take less of the base. There's only one of them that's possible for answer D. And this one got a lot of people. How much faster would argon effuse compared to chlorine gas? Well, argon has a molar mass of 40. Chlorine gas is not 35 and a half. It is about 71, because chlorine is a diatomic gas. So the rate of argon over the rate of chlorine is actually going to be the square root of 71 over 40. It's very good that you realize the number should be greater than 1. But however, you flip the order in order to make it greater than 1. So the answer should be 1.33. That got a lot of people. So don't feel bad if that tricked you. Chlorine is one of the 4 or 5 diatomics out there. What is the enthalpy of the following reaction? This should be more or less straightforward. You have to do products minus reactants. Don't forget that there's 2 silver chlorides and 2 silver nitrates. So products, all my products, let's see, products is negative 127 times 2, because there's 2 of these guys, and magnesium nitrate, negative 881.7. So let's calculate that real quick. 881.7. You have negative 1135.7. For the reactants, you have negative 313 times 2 and negative 801.3. So you have negative 1427.3. So 1135.7 minus 1427.3. You get a positive 291.6, or B. 291.6, or answer B. Enthalpy of the following reaction. So what is enthalpy of acetic acid breaking apart? The dissociation of acetic acid. Well, we have to look. These 2 guys are in the correct places, in the correct values, so we can use the equation as written. This guy is on the opposite side, so that means I have to flip it around. So I'll say negative 60.37 plus 55.8, your answer becomes negative 4.57. 4.57. Negative 4.57. It produces heat, but not a whole lot. In glass making, sodium carbonate is added to create flux. Sodium oxide. How much sodium carbonate do you need to generate 75 grams of sodium oxide? So grams to moles to moles to grams. 75 grams of sodium oxide. So 23 times 2 plus 16 is 62 grams in 1 mole. For every 1 mole of sodium oxide, you would get 1 mole of sodium carbonate, and then we'd use the molar mass of sodium carbonate. So we'd have to add on to that 62, we'd add on 2 more oxygens, 32, and a carbon, 12. So the molar mass is 106 grams in 1 mole. So out of 75 grams, you should have a number that is greater than 75 grams. So the correct answer is 128 grams. So A and C are incorrect right out of the bat. If you think about it, A and C are incorrect right off the bat because they are less than 75 grams. In the combustion of 100 grams of glucose and 100 grams of oxygen, what is the limiting reagent? Well, the molar mass of glucose, 12 times 6 plus 12 times 1 plus 6 times 16 is 180 grams per mole. The molar mass of oxygen is 32 grams per mole, but you need 6 moles of oxygen. So 100 divided by 180 means how many times can this reaction go? How many times can this reaction go with 100 grams based on the glucose? You can do the reaction exactly 0.5 repeating times with that amount of glucose. However, same amount with oxygen, 1 mole, but you have to go, for every time you run the reaction, you use 6 moles of oxygen for 1 reaction. So 100 divided by 32 divided by 6 should be, we can run the reaction only 0.521 times. So which one runs out first? Actually, it's oxygen. Then what pressure in bars would be generated by 5 moles of ideal gas at 280 Kelvin stored in a 1.5 liter container? Literally, P equals nRT over V. P, 5 moles. R, 0.08314. T, 280. V, 1.5. 5 times R times T divided by V gives us 77.59, which rounds to 77.6. So the correct answer is A. This one, a little bit more challenging than, say, on the old test, but still not too challenging. The planet Venus has an atmosphere of 93 bars. Contains 96.5% CO2. What is the rest of the gas being? Essentially nitrogen. What is the partial pressure of nitrogen on a Venus? Step 1, figure out that if 96.5% is CO2, how much is nitrogen? It's 3.5% nitrogen, because 100 minus 96.5 is 3.5. Then you would take the 3.5 divided by 100 times your 93 to get what is your pressure. So 0.035 times 93, you would have about 3.255 bars of nitrogen pressure. Moving right along to number 12. 85 grams of metal absorbs 1500 heat. The temperature warms from 10 degrees to 55.8. What is the specific heat of metal? There's a Q equals MCAT, except this time we're finding the C. So Q is 1500 joules. You divide by your mass of metal, 85 grams, and your delta T of metal, which is essentially 55.8 minus 10 equals our heat capacity, which is essentially 45.8. So 1500 divided by 85 divided by 45.8 gives you 0.385. 0.385. So answer B. Once again, metals typically like a heat capacity of lower than 1. So A and B are probably the best answers. But B is the correct answer. 117 grams of calcium carbonate is dissolved in enough water to make a 2.5 liter solution. What is the solution's molarity? This we're going grams to moles to molarity. First things first, 117 grams. We got to turn this to moles. Calcium, if I'm not mistaken, is 40. Carbon is 12. Oxygen is 16. There's 3 of them, so 48. The molar mass is about 100. 100 grams in 1 mole. Then I divide by a volume of 2.5 liters to get it moles per liter. So 117 divided by 100 divided by 2.5 gives you 0.468. So answer C. A gas has a pressure of 720 torr at 250 mils. What would the pressure be at 180 mils? So, trick question. You don't need to convert torr. This is a P1 V1 equals P2 V2. So 720 times 250 equals P times 180. Volume went down, so pressure should go up. So 250 divided by 180. Surprise, surprise. This one's actually answer D, 1,000 torr. Seems like too perfect of a number, but that is the case. 1,000 torr. Because volume went down, pressure should go up. Really, A and D are the only possible answers. What is the percent yield if we use 480 grams of iron oxide in excess of coal and oxygen? We produce 300 grams of iron. So actual divided by theoretical. So we need the actual, we need the theoretical. Well, this one I actually gave in class, though I doubt many of you remember. 480 grams iron oxide. Iron oxide weighs about 160 grams in 1 mole. For every 2 moles of iron oxide, we produce 4 moles of iron. And iron is about 56 grams in 1 mole. So you do that, 480 divided by 160 times 4 over 2 times 56 gives us 336. 300 divided by 336 times 100 is 89.3. Answer D. So D and D. Last one here. What is the density of 1 atmosphere of air? Molar mass 28.97 at 9 degrees C. Step 1, add 273 to get this into Kelvin. So that makes that 282 Kelvin. Density is equal to P times molar mass over RT. So 1 ATM times 28.97 divided by R, 206 and 282. You do that, should get a density. 206 divided by 282, and you have, wait a tick. Here's my problem. I used the wrong molar mass. 28.97. Yet 1.25. Answer C. Finally, for this page, what would the enthalpy of formation be for hydrogen gas? I could have asked for any element because the enthalpy of formation of a pure element is calculated from what energy would it take to do this reaction? H2 gas to H2 gas. Well, products minus reactants, the products and the reactions are the same. The energy would be 0 kilojoules. That is the definition of enthalpy of formation for any element in the standard state. Water, on the other hand, would be H2O. How much energy would it take to form that from H2 gas and 1/2 molecule of O2 gas? That would be different. But this guy, a pure element, is 0. It's always going to be the case. A pure element in its standard state is 0. There's no other way to solve that. That's the one thing you might be expected to know, that the enthalpy of formation of a pure element is 0 and always will be. Last page. Set up the work for this problem. So literally, no need to actually solve. How many grams of oxygen would be needed to react with 37 grams of methane? 7 grams of CH4. Well, carbon is 12. Each hydrogen is 1, so the molar mass is 16 grams and 1 mole. For every 1 mole of methane, there's 2 moles of oxygen that it will be needed. And for every 1 mole of oxygen, it would weigh 32 grams. That's all I asked for. If you went on to solve this and say this would weigh 148 grams of oxygen, that's great. But you don't need to do that for us. Considering the van der Waals equation, P equals nRT over V minus NB minus AN squared V squared. Would a large attractive force result in a larger or smaller pressure compared to the ideal gas? So ideal gas is missing that term, and it's missing the NB. The attractive force is A. Your attractive molecular force A. Would a large A result in a larger or smaller pressure? Literally, you just need to plug a number in and think about it. If A was 50, any number minus 50 times whatever this fraction is, would that be larger or smaller than it initially is? If this was, and hopefully you'll say any number minus a positive number would be smaller. So the correct answer is B, smaller. Last one. It was a kind of supposed to be a fun little trick question. It did not mean to be so freaking hard. Based on the problem number 1 in chapter 10 homework, we look at a particularly wordy professor is blathering on during the lecture, turning oxygen into carbon dioxide under 1 bar of pressure via the following equation. Glucose plus 6 oxygen goes to 6 CO2 and 36 ATP and 6 water. Work is traditionally defined as pressure, negative pressure times the change in temperature, change in volume. Approximately how much work is the professor doing? It's supposed to be a joke, people. You don't have enough information to solve this in any other way. I threw up impossible numbers that there's no way for you to find these otherwise. Those are just numbers I made up, and yet I still tricked so many of you. The idea here is that we only look at the gases. The gas is expansion of gas is doing work. We have 6 oxygens on the left. We have 6 CO2 on the right. Which side has more gas? Well, the answer is neither. So how much expansion could possibly be going on in an ideal gas situation? The change in volume is approximately 0. If the change in volume is approximately 0, work must be 0. It's a joke that's saying us as professors are doing no work. I'm sorry that has turned into such a difficult problem for you. It was supposed to be easier. That is test 4. I will see you for the final. Have a good day.